So let's have this example. So first of all, we have a horizontal block weighing 12 kgs. It is supported by 3 rods, 2 steel rods, and a bronze rod. So these are the properties of each rod. Then for this example, we are considering the change in temperature or the deformation due to change in temperature. So we are looking for the stress carried by the steel and the stress carried by the bronze rod. So if we are computing for the stress caused by this 12 gigs, we need to compute for the force carried by the steel and the force carried by the bronze. So if we are to apply the equations of equilibrium, let's say summation of forces vertical equals 0, upward forces to be positive. So we will be assuming that the forces carried by the steel will be upward, while the force carried by the bronze is also upward. The same with this one, also upward. So summation of forces vertical, we have two forces to be carried by the steel rods, plus the force to be carried by the bronze rod should be equal to the weight of the block, that is 12 gigs, or it's the same as 12,000 pounds. So that will be our first equation. So summation forces horizontal and summation of moments will not be applicable for this problem. To compute for the unknowns, for this one, this is a statically indeterminate problem. So therefore, we have to apply the concept of strain. So for this one, for this block to be horizontal, since we have a symmetrical support, there will be an elongation for the steel, or deformation for the steel, deformation for the bronze, the same with this one, deformation of the steel. So for this block to be horizontal, the total deformation of the steel should be equal to the total deformation of the bronze. So what will be the equivalent of the total deformation? That will be first the deformation because of the load to be carried by each rod plus the deformation due to change in temperature. Take note, we have a change in temperature. Let's say this is an increase in temperature equal to 100 degree Fahrenheit. So how do we compute for thermal deformation? This is equal to the change in temperature, alpha. This is the coefficient of thermal expansion multiplied by the length. So how do we compute for the deformation due to load? From our previous discussions, this is the force, the length divided by the area times the modulus of elasticity. So we are considering two components of the total deformation. So we have what will be the total deformation of the steel. The total deformation of the steel, this is first due to temperature plus the deformation due to load for the steel will be equal to the total deformation of the bronze. That is the deformation due to temperature or change in temperature for the bronze and the deformation due to load for the bronze. So let this be our key equation. So let us compute for the deformation due to change in temperature for the steel. We have delta, an increase in temperature equal to 100 degree Fahrenheit, multiplied by alpha. What is the alpha for steel? We have this as 6.5 times 10 raised to negative 6 per degree Fahrenheit. Then multiplied by the length. What is the length for the steel? Okay, the length is 2 feet. We are multiplying 12 for the unit to be in inches. So this is the deformation due to change in temperature. Then plus, we have the deformation due to load. That is the load to be carried by the steel. What is the length of the steel rod? That is 2 feet. Multiplying by 12 to be in inches. This is divided by cross-sectional area of the steel is equal to 0.75 square inches. Then multiplied by the modulus of elasticity, we have 29. This is 29 times 10 raised to 6 pounds per square inch. So this is the total deformation for the steel should be equal to the deformation due to change in temperature for the bronze. That is, we have 100 degree Fahrenheit multiplied by, for alpha for the bronze, this is 10 times 10 raised to negative 6 per degree Fahrenheit. Then the length of the bronze rod is 3 feet multiplying 12 to be in inches. This is the deformation due to change in temperature for the bronze. Then plus, due to load, this is the load to be carried by the bronze multiplied by the length multiplying 12 to be in inches divided by cross-sectional area is 1.5 square inches. Modulus of elasticity for the bronze. This is, we have 12 times 10 raised to 6 pounds per square inch. Okay, as you can see, we converted some units to be consistent in units. So we have, let's have this value, that is 100 multiplied by 6.5 times 10 raised to negative 6 multiplied by 2 times 12, 24. So that value is equal to 0.0156. Then plus, the next term will be in terms of the load to be carried by the steel. That is 24 over 0.75 multiplied by 29 times 10 raised to 6. So this is equal to the load to be carried by the steel over 906 250. Then equal to, for this term, what is that value? We have 100 multiplied by 10 times 10 raised to negative 6 multiplied by 36. That is equal to 0.036. Then plus, for this term, in terms of the load to be carried by the bronze, that is 36 over 1.5 multiplied by 12 times 10 raised to 6. So we have that as the load to be carried by the bronze divided by 500,000. So we may now express one unknown in terms of the other. So let's say I'll be expressing the equivalent of the load to be carried by the steel. In terms of the load to be carried by the bronze. So we have that as the load to be carried by the steel is equal to 0.036 minus 0.0156, 0.036 less 0.0156, then multiplied by 906,250. So 906,250. So we have the value as 18,487.5 plus. So let's have 906,250 divided by 500,000. So I'm just doing a simple algebraic operation. That is 906,250 divided by 500,000. And that is equal to 1.8125 of the load to be carried by the bronze rod. So we have our equilibrium equation a while ago. This is the 2 times the load to be carried by the steel plus the load to be carried by the bronze is equal to the total weight of the block, 12 gigs or 12,000 pounds. Let us just substitute the equivalent of the load to be carried by the steel. This is twice of 18,487.5 plus 1.8125 of the load to be carried by the bronze, plus the load to be carried by the bronze rod is equal to 12,000 pounds. So let us compute for the value of the load to be carried by the bronze rod. So this is the same as 12,000. 12,000, if you have to transpose this one, the sign will be negative. Minus 2 times 18,487.5. That is equal to negative 24,975 divided by twice of 1.8125 plus 1. So divided by twice of 1.8125 plus 1. So we have the value of the load to be carried by the bronze is negative 5,400 pounds. So which means we have a wrong assumption. So the load to be carried by the bronze rod is under compression, and I think it's supposedly it is downward. Since we assume initially that it is upward. So negative 5,400 pounds, which means it should be, the direction should be downward. So computing for the load to be carried by the steel, this is twice the load to be carried by the steel plus the load to be carried by the bronze is negative 5,400 is equal to 12,000 pounds. This is the load to be carried by the steel is now equal to 12,000 plus 5,400 divided by 2. So we have that value as 8,700 pounds. Take note, so these are the load to be carried by each rod due to the given load. Due to the given load, 12 kips. So how do we compute for the stresses per material or per rod? So this is for the steel. We have the stress for the steel is equal to, we have the load is equal to 8,700 pounds. Cross-sectional area of the steel is equal to 0.75 square inches, or square inch. So we have 8,700, this is divided by 0.75. We have that as 11,600 pounds per square inch. Then for the bronze, we have the stress for the bronze rod is equal to, we have a compressive force, this is negative 5,400 divided by cross-sectional area is 1.75 square inches. And this is equal to, so negative 5,400 divided by 1 point, I think it's 1.5, not 1.75. So the cross-sectional area of the bronze rod is 1.5. So we have that as negative 3,600 pounds per square inch. So the stresses for the steel, it is under tension, and for the bronze rod, it is under compression. So this will be our solution.